So thanks for the introduction again, Ian, and thank you, Ian and Rob, for the kind invitation. I'm very pleased to be here. Hi, everyone. I'm very happy to present our recent work on displacement flows in rotating pipes, which is pretty recent. And I would like to hear your feedback and comments on our work to improve it. So if you see my webcam video in the middle of the presentation, you can use the side-by-side mode in the Zoom so that I move away from your view. So in this presentation, I will provide an overview of displacement flows and basically the ways and the methods to improve the displacement efficiency. Then we will talk about an application of displacement flows in a rotating pipe. Then we will move to the main body of the presentation, which is the experimental results and simulation results on displacement flows in an axially rotating pipe. And I will end with a brief summary. So let's first start with the overview. Displacement flows occur in many natural phenomena and industrial processes. For example, sugar refining, beverages industries, printing devices, enhanced oil recovery, oil well cementing, and cleaning of equipment. In these processes, one fluid usually displaces another fluid, and the objective is that the displacing fluid should completely remove the displaced fluid. The processes in terms of the displacement that I just mentioned can be simplified to the configuration that you can observe. We have a red drilling fluid that must displace a light displaced blue fluid, and the two fluids have different properties. So in this case, an ideal or dreamlike situation is that the displacing fluid completely basically removes the displaced one, and you can have a 100% displacement efficiency. But this case almost never happens because the interface is not actually very much friends with us. And what we have is a variety of interfacial instabilities. And I show two examples of what can go wrong. For example, if you have a less viscous fluid displacing a more viscous one, you can have a finger of the displacing fluid in the middle of the displaced fluid. Or if you have a heavier fluid displacing a lighter fluid, you have a slumping pattern. And these both cases are failing basically in terms of the displacement, and the displacement efficiency is very low in these cases. On the other hand, you can play with some of the flow parameters to enhance the displacement efficiency. For example, you can play with the fluid properties such as density, viscosity, rheology, miscibility, and so on. Or you can try to basically manipulate the flow geometry, use different types of geometry, incline the geometry, manipulate the geometry by inducing wall non-uniformity, converging, diverging channels, type things. You can induce some motion on the flow geometry, or you can change the surface properties. So all of these are with the hope to improve the displacement efficiency. In our group, we have tested a variety of methods to basically enhance the displacement efficiency for different types of flows. For example, in these works, we have considered the geometry type. In a few papers, we have looked at rectangular channels, horizontal and vertical pipes. In some other works, we have looked at the effect of inducing a small non-uniformity along the flow, for example, non-uniform helical cell or non-uniform, for example, channels. These areas have benefited from the contributions of my postdocs, Ali Eslami and Ruzbeh Molla Abbasi. In collaboration with Professor Larachi, our colleague, we have, and basically two PhD students, Jian Zhang and Amin Amiri, we have used a hexapod robot to induce various motions on the geometry, for example, rotational or translational oscillations. and to see how this affects the displacement efficiency. Using this hexapod robot, it's even possible to make the flow geometry dance, as you can see in this short animation. So we have also tested inducing wall slip on the flow geometry in my work with my PhD student Hossein Rahmani. Ali and I have looked at the effect of wetting, for example, effects on how it improves the displacement efficiency, and these are published in a few papers. And our latest method basically is including or applying a pipe rotation to improve the displacement efficiency of our flows. This has been by far our most successful method to improve the displacement efficiency, and this is going to be the topic that I'm going to talk about. This is the work of my PhD student Sean Leo, who just graduated a few months ago. And in this work, Mahdi Izadi, who is a PhD student of Ian Frigard, collaborated with us in the initially setting up the numerical simulation. Of course, there are a variety of other methods in the literature to improve the displacement efficiency or controlling the flow. But this has mostly focused on simplified geometries such as helical cell and controlling only viscous fingering type flows. For example, using the tapered flow geometry, inducing injection rate variation, elastic wall boundaries that to control, for example, the displacement, applying electrical or magnetic fields, using geometrical flow motion, which is known as lifting helical cell, or the use of chemical reactions for inducing macroscopic diffusions. I would be happy to be reminded of other types of ways to improve the displacement efficiency if I'm missing a major basically aspect. But briefly, these works basically can be viewed in terms of improving the displacement efficiency. And some of them are more successful than the others. But the thing is that it's not clear to what degree their results can be extended to more realistic configurations, because the geometry considered is simple and basically it's just a helical cell. So with that, let's move on to the main topic of our work, and starting with the industrial application of displacement flows in a rotating pipe. Buoyant displacement flows occur in, for example, one particular example is the primary cementing of oil and gas wells, in which a drilling mud must be basically removed from the casing of the geometry. Basically, this is a pipe, and the drilling mud must be removed from this pipe by pumping a sequence of fluids into the well. And the partial or incomplete removal of the drilling mud may result in sealing and isolation issues, and it may also lead to catastrophic consequences, such as what we observed in 2010 in the Gulf of Mexico. And this is the time actually I called Ian when I was in France. I said something terrible happened, but it was due to the primary cementing going wrong. So the process parameters are many: the viscosity and the density ratio between the two fluids, miscibility and mixing, well inclination angle, and viscoplastic effects of the drilling mud. These are all basically parameters of the flow. And in some cases, the rotation of the casing, which is a pipe, at rotation rates of 10 to 60 RPM can be used to improve the displacement efficiency and improve the process. But in the scientific literature, there is not much information on that. So, excuse me. So in the scientific, in terms of the industrial context, a scientific problem can be defined in terms of a simplified flow geometry that you can observe. And we consider a buoyant miscible displacement flow in an axially rotating pipe. We simplify the process by assuming that the displacing fluid, the heavy fluid, is only Newtonian, and the light fluid can be Newtonian or viscoplastic. Even with this simplification, we can see that there are, and a dimensional analysis actually will reveal that there are many parameters, up to 10 parameters, 9 or 10 parameters that govern the fluid dynamics. So these include the Reynolds number, the Rossby number, Atwood number, Freud number, inclination angle, viscosity ratio, Bingham number, Peckley number, and the aspect ratio. So we would need to make more simplifications to this problem so that we can make the analysis of the flow possible. In this approach, for example, we consider a small density difference between the two fluids that we are considering, so that the Atwood number would be not relevant, but it would be very much relevant when it comes to the force of buoyancy. We assume that the inclination angles are in the moderate range, so they are comparable and they are sort of ordered one parameter. For the viscoplastic displacement, we assume that the viscosity ratio is very large. We also assume that the Peckley and the aspect ratio are both very large. So what we end up with would be 4 parameters, which in the dimensional sense explain the impulse flow, the rotation, the pipe rotation speed, the buoyancy, and the yield stress. So let's move on to the research results. And as I explained, we want to understand the effects of 4 parameters. So the buoyancy, rotation, impulse flow, and the yield stress. And to systematically analyze the flow, it makes sense to start with the simplest case, which is the Newtonian exchange flow, which means that we basically neglect the effect of impulse flow. Impulse flow is 0, and the yield stress is also 0. And we basically increase the complexity in the following parts of the presentation. So for the exchange flows, only buoyancy and the rotation basically explain the flow. In terms of the experiments, the experimental schematic of the experiments can be observed in this schematic. As you can see, we have a long inclined pipe with a gate valve to separate the pipe into 2 equal parts, to separate the heavy and light fluids. These fluids are glycerin water mixtures or salt water. The pipe can be rotated at any rotation angle up to 100 RPM. In a typical experiment, the gate valve is opened and simultaneously the pipe rotation at a constant rotation speed starts. A camera takes side view images, and for a few experiments, we also show some top view images of the process using some mirrors. A UDV and ultrasound Doppler velocimeter also provides the velocity profiles in a given, basically the axial velocity profiles in a given cross section of the pipe. So the parameters of the experiments in dimensional forms are given. So the inclination angle, the kinematic viscosity, Atwood number, which is the buoyancy basically, and the rotation speed. As a complementary approach to our experimental approach, we run actually numerical simulations using OpenFOAM. And in this case, we solve the governing equations, including the continuity, the concentration diffusion equation, and the momentum equations. And we have some assumptions, for example, miscible Newtonian fluids, small density difference, a small molecular diffusion, and we use finite volume method in combination with VOF and a range of established solvers to basically solve for the flow. And in terms of the meshes, we use a moderate cell numbers of 10 million. So let's jump into the experimental results, looking at the basically an image sequence of the flow in the absence of the rotation. And we are showing only what happens below the gate valve because the flow has a twofold symmetry with respect to the gate valve. So it's basically symmetric. What we observe is that as the gate valve is opened, The heavy fluid slumps underneath the light fluid and it moves basically downward. The axial buoyancy component, basically, which is in this direction, basically keeps the two fluids more or less segregated, although we have some Kelvin-Helmholtz type instabilities at the interface. And this is basically a classical gravity current. So let's see what happens in the presence of rotation. And looking at the side view of the same experiments that I showed, by increasing a small rotation, we observe that the rotation inertia cannot basically overcome the transverse buoyancy, and so the fluids only slightly mix and the front velocity slows down. By increasing a bit of the rotation, what we observe that the fluids transversely mix more efficiently, but the mixture maintains a density contrast that basically moves the flow forward. At the largest rotation, what we observe is that basically the fluids very efficiently transversely mix, and the buoyancy force slows down or gets reduced, and the front velocity slows down, and it eventually stops. So the propagation of the fluids stop at a propagation distance with respect to the position of the gate valve. Comparing the top and side view of the same process, we can observe that at zero rotation, they are completely different. As we expect, we are looking at the side and top, they are completely different. But by increasing the rotation, they progressively become more similar, and at the largest rotation, they are nearly identical, meaning that the flow has basically it implies the homogeneity of the mixing in the rotation pipe. So let's also look at some axial velocity profiles in the case of small and moderate rotations in the position of the UDV. So I'm just going to mark the position of the UDV where the velocities are measured. So in both cases. And we are showing 5 basically snapshots of the experiments and the corresponding velocity profiles. So what we observe is that before the front reaches the UDV position, the velocities, axial velocities are nearly zero. As the front reaches the UDV position, we observe a counter current flow, which gets enhanced as the front has passed the UDV position. And at larger rotation, we observe that the velocities are significantly reduced, and the asymmetric velocity profile corresponds to a local mixing zone between the two fluids. So now let's look at the long time front velocity, so the velocity of the penetration of the fluid at long time, and we plot it versus the rotation speed. And what we observe is that by increasing the output number, so this is in this direction, the front velocity increases due to the buoyancy, but at the same time, by increasing the rotation speed, the front velocity decreases until it reaches basically zero at sort of largest rotation speed. We also observe that the kinematic viscosity and the inclination angle do not much affect the front velocity, as our dimensional analysis also suggested earlier in the talk. So it's useful to try to understand what governs the front dynamics. So to do so, let's start with the case of basically the absence of mixing, and write a balance between the characteristic buoyant stress in the longitudinal direction and the inertial stress that balances it. So this gives us basically a ratio that can be said to be a characteristic inertial buoyant velocity, a square root of ATGD, which is the only parameter that governs the flow in the absence of the mixing. And that would be, and the front velocity would be only a function of the inertial buoyant velocity, characteristic inertial buoyant velocity. In fact, the previous works in stationary rotating pipes, for example, the now classical works of Seon, show that the front velocity in intermediate angles are very close to the value of the VI that we have obtained. So what happens in the presence of rotation and mixing? We know that the mixing between the two fluids due to the inertial rotation, due to the inertia caused by rotation, basically reduces the longitudinal buoyancy force that drives the flow. So this can be written in terms of a balance between the longitudinal buoyant stress and the characteristic inertial buoyant stress at the front. And in this case, delta rho is basically showing the local density difference, which is a function of mixing. So it's clear that another balance that relates the flow to the transverse mixing should be written. So in this case, we can basically write a balance between the transverse buoyancy, which separates the two fluids in the transverse direction and wants to keep the interface horizontal and keep the fluids basically separated and segregated and avoid mixing. And on the other hand, we have inertia due to the rotation, which wants to tilt the interface, overturn the interface, and mix the fluids significantly. So the balance between the two cases in terms of the stresses can be written simplified in terms of omega r times square root of ATGD. The numerator is the characteristic, basically rotational velocity, and the denominator is the characteristic inertial buoyant velocity. So far we know that, or we have found that the relevant dimensionless groups in the flow are Vf over Vi that we observed in the absence of the rotation, and the V omega over Vi in the presence of the rotation. So if indeed, if we plot our data, experimental data in the plane of Vf over Vi and V omega over Vi, we observe that we get a reasonable collapse of the data points, except for when V omega over Vi gets very large. And we can simply fit basically a second order function in terms of the Taylor expansion of the in terms of the Taylor expansion with respect to V omega over Vi, and see a reasonable agreement with the fit. So let's go to the talking about the propagation lengths or propagation distance. We have observed before, and we can also see in this image sequences that the front velocity basically slows down and eventually stops at some propagation distance with respect to the gate valve. Let's call it L. And this L significantly decreases with omega, and it finally reaches a small value at a very large omega. So if we use the proposed dimensionless groups of V omega over Vi, we can get a sort of reasonable collapse of data. And that basically, we can fit a power law to this basically collapse of data and try to predict the propagation lengths in a reasonable manner. Analogous to the propagation lengths, we can define a propagation time, basically, which is a time when the large scale penetration of the or interpenetration of the fluids stop. And this would be basically plotting this versus omega shows that the propagation time also significantly decreases with omega. And this time, if we make the time dimensionless with the characteristic buoyant inertial time, and again we use V omega over Vi, we are able to get a reasonable collapse of data and predict the propagation time. So we have so far attributed the decrease in the front velocity to the rotation effect, to the mixing between the two fluids. But this alone cannot explain why the propagation or the large scale penetration of the fluid stop at large rotation. So in this example, snapshot, what you can see that at large rotation, distinct density contrast still exists in the flow, and in the absence of the rotation, one could argue that such a density contrast could induce actually an exchange flow between the two fluids. So to test this hypothesis, we have plotted, we are providing three experimental examples of the spatial temporal diagrams of the depth average concentrations. And in this experiment, we are stopping the rotation at a certain time after the large scale, basically propagation of the front has stopped. So we stop the rotation at some time. And what we observe is that the previously stagnant front gets remobilized when the rotation has stopped. And this implies that the rotation alone cannot, the mixing alone and the reduction of the buoyancy force cannot alone explain the complete stoppage of the flow. So let us try to explain why this stoppage occurs. And let's look at some numerical simulation results of the concentration contours in the axial plane of the pipe, and for the same experiments that we are showing. So what we observe is that initially the fluids are segregated, but they start to mix, and eventually they mix very significantly, and at some basically longer times the larger scale propagation stops. But again in the simulation we observe that distinct density contrast between the two fluids persist. So what happens? One way actually to qualitatively explain the complete stopping of the flow in this case is to use the Taylor-Proudman theorem, which states that at large, basically at very large rotation, the Navier-Stokes equations are simplified to a balance between the Coriolis force and the pressure gradient, which after taking a curl simplifies to du by dx equal to 0. So this means that there is an axial sort of structure in the flow, sort of an axial rigidity in the flow, and a columnar structure in the flow that stops the larger scale motion of the front. Another way to qualitatively and very crudely explain the phenomena observed is looking at the cross section, for example, somewhere in the mixing zone. And in this case, the rotation axis is towards us. So let's assume that a piece of fluid wants to or has to basically move in a certain direction to be regrouped by some other pieces of the fluid to be able to create a large scale, basically overturning of the interface. In a moving frame of reference, this piece of fluid would experience a Coriolis force in a perpendicular direction that would limit the movement in the desired direction. So basically, since this is true throughout the cross section, the heavy and light fluid pieces cannot organize themselves or create large structures in a way to create large basically penetration and large overturning of the interface and create a bypassing of the fluids in the let's say transverse direction. So this is another crude way of explaining why the interpenetration stops. A way to visualize the application of Taylor-Proudman theorem is through putting an obstacle in a rapidly rotating fluid. The obstacle creates a column of stagnant fluids, which is referred to as Taylor column. So you can see the tracer moves around the column and avoids the Taylor column. So basically as you saw, the dyed fluid goes around the column. So this basically emphasizes the axial rigidity and the columnar structure of rotating flows in general and our flows in particular. Another application of the Taylor-Proudman theorem is in the inhibition of Rayleigh-Taylor instability, which has been considered in some recent works. So a heavy fluid on top of a light fluid in the absence of a rotation in a cylinder shows actually some Rayleigh-Taylor instability, but by increasing the rotation, we observe that these instabilities are further are reduced. They never die, but they are very much reduced. So let's move back to our own numerical results. Basically, given here, we are looking at the concentration contours, axial velocity and axial velocity contours and velocity vectors in the axial, basically plane of the pipe, and also in one cross section that I marked. This is marked by a small arrows in. So the cross section is here in all cases. And what we observe is that by increasing the rotation, the flow is a lot affected by the rotation, and at large rotation, basically the rotation completely dominates the flow in for example, in this case that you can observe. So it's useful to look at, or it may be interesting to look at the isosurface representations of the concentration values equal to 0.5, which would represent the pseudo interface in our simulations. And we are showing a gradual increase of the rotational speed for these simulations. And these are corresponding to these basically image sequences. So what we are doing, we are looking at through the pipe through this point of view. Okay, so what we can observe through this point of view is the position of the front or shape of the front and the interface at the between the two fluids, and this basically the flow is coming towards us. So you can basically imagine it that way. So by increasing the rotation, we can see that the position of the front, basically, or the shape of the front is changed, and the front moves sideways in the direction of the rotation. And by increasing the rotation, interfacial instabilities basically get enhanced due to the rotational inertia. And what we observe is that at the largest rotation, the front shows actually sort of a shape of a spiral. So let's move now to the next or second section of the presentation, which is Newtonian displacements in a rotating pipe. So the difference between this case and the exchange flow is that now the impulse flow is non-zero. So we are adding an impulse flow to the system, but the yield stress, we keep it at 0 in this case. So the schematic of the experimental setup is the same as before. The only main difference is that we have a much longer section below the gate valve. And due to the impulse flow, the flow is not symmetric anymore. So it's useful to distinguish between a lower front with the velocity Vf at long time moving downward and an upper front with velocity Vt at long times. And the experimental ranges and parameter in dimensional form are also given. So let's jump into the results in terms of the general flow behaviors. In the absence of the rotation, what we observe is that as the gate valve is opened, the heavy fluid slumps underneath the light fluid, and it moves, the lower front basically moves downward, and a counter current flow is observed. So if you look carefully, you can see also the upper front moving upward. So if you increase the rotation, what we observe is that the transverse mixing between the two fluids increases due to the rotation inertia. So in this case, the lower front moves downward, but there is no upward motion of the upper front. If we increase the rotation slightly further, we can see that the fluids are very much transversely mixed, and in this case, the lower front moves downward, and the upper front also starts to move downward. And if we increase the rotation even further, we observe that the fluids are significantly mixed, very efficiently mixed transversely. And in this case, the lower front moves downward, and the upper front also moves downward. And this case basically represents a complete efficient displacement flow. That was what we were looking for from the beginning. So it makes sense to plot the variation of the upper and lower front that we just observed this is the lower front, this upper front, the variation of these front velocities at long time. So if we plot the lower front velocity versus omega, we observe that the front velocity actually decreases with omega and then reaches a constant value of 1.3 times v0 at large omega, and the upper front velocity starts at negative values, crossing 0 and then going to positive values and eventually reaching a constant or nearly constant velocity of 0.8 times v0. And these sort of constant velocities, so these thresholds are representing where we transition to a regime of complete removal of the displaced fluid. These results that I'm showing here are basically the same phenomena, but for another value of the impulse flow and a large range of parameters showing the same trend and same sort of results. So what we observed or what we have seen in early results was that by increasing the rotation, the fluids transversely mix, and this transverse mixing of the fluids results in the reduction of the front velocity and the reduction of the front velocity due to buoyancy. So in this case, one can argue that if we want to analyze the flow on how the displaced fluid is removed at high rotation, we can say that, for example, if we sufficiently, so we have the interface between the two fluids, if we sufficiently mix the interface or destabilize the interface in the transverse direction, right? And then induce a strong enough impulse flow. So we mix the fluid transversely and induce a strong enough impulse flow, we should be able to remove the displaced fluid from the domain. So we can write a balance between the basically two stresses, a buoyant stress in the longitudinal direction, which should be basically, which resist the impulse flow, inertia due to the impulse flow, and a balance between characteristic stresses in the transverse direction, which, as I mentioned for the exchange flow results, for example, in the transverse direction, wants to keep the fluids segregated and separated and avoid mixing, and the transverse inertia that wants to overturn the interface and induce mixing. So basically, we have two different balances, and the ratio between the first set of stresses can be written in terms of the balance between two characteristic velocities, so V0 over Vi, characteristic impulse velocity and characteristic inertial buoyant velocity, which can be equivalently explained versus the Fruit number. And the second balance will give us the same ratio as we had before for the exchange flow, which is V omega over Vi, which can be equally represented versus Fruit number over Rossby number. So if our analysis is correct, the flow removal, the removal of the displaced fluid should be basically, we should be able to explain it versus the Fruit number and Fruit over Rossby number. So indeed, we observe that by plotting our experimental data in terms of efficient removal and inefficient removal in the plane of Fruit versus Fruit over Rossby number, they are completely segregated. And basically, a straight line that is basically given here can explain or delineate the transition between the inefficient removal regime to the efficient removal regime, which is most of the data. And using basically this relation, we can find a critical Rossby number that basically governs the transition between inefficient and efficient displacement flow regimes. So these were my results for the displacement flow. But before I move on to the viscoplastic results, I would like to show some interesting results on how the rotation overcomes the transverse buoyancy using 2D simulations. It means that there is no axial flow in these simulations that I'm going to be showing. So we start with a flat interface separating the heavy and light fluid in the middle. So I let you watch the videos. So what we observe is that at the smallest rotation, the transverse buoyancy means and the two fluids do not mix much transversely. At the highest rotation, the rotation means and the two fluids completely mix. And at the moderate or transitionary rotation, the interface is at the verge of overturning. And this basically critical condition can be estimated to be at the fruit of a Rossby number of nearly 1, which is basically in agreement with our previous observations. Conceptually similar flows to this can be seen in the context of granular flows in rotating drums. But our case is slightly different because there are interesting recirculations in the flow that makes the shape of the interface resembling to a yin and yang symbol. So I think it has something to do with my PhD student having Chinese origin, but maybe I'm wrong. But this is this is quite interesting. Just one more thing before going to the viscoplastic results. I would like to open a parenthesis and mention some of the other areas of rotating flows. Of course, I'm not presenting anything on the geophysical flows because there are hundreds of papers in geophysical flows because of the rotation of the Earth. But those are mainly on unconfined flows, and the scales are different. So mainly for limited and sort of confined flows, there are some interesting works in reaming flows, which is a thin layer rotating in a cylinder. We have some hot topics on rotating Rayleigh-Benard convection flows, mostly on turbulent flows. And a classical area is a rotating Poiseuille flow, starting with the stability analysis of Pedley and the extension of that to other situations. Of course, there are reviews in this context, and there are also stability analysis of Taylor-Couette flows for Newtonian flows, extensions for viscoplastic flows, and also extension to thixotropic flows. A different context, but still relevant in terms of the dimensionless numbers, could be jet flows due to rotation, which is an area that my PhD student Suran Nuruzi and I have worked on. And there are a lot of very interesting spiral motion of these flows published in our recent papers. And also there is for me at least personally, an interesting area where I'm studying my rotating twins. So I have a lot of discoveries, but I will make them clear in my next presentations. So let's move on to the viscoplastic results, which are shorter because of the time, but I can explain further if needed. Before diving into the results, let's try to understand what the literature tells us in terms of displacements in stationary pipe. Non-buoyant displacements have shown the presence of corrugated, wavy, and smooth displacements. Buoyant displacements of viscoplastic fluids have shown a slump type and center type displacements. And the recent work of Amiri has shown that if you increase just a single parameter, the yield stress in the fluid, you can achieve a variety of different displacements. So briefly, these works show that static residual layers, as you can see in these images, static residual wall layers can appear in these flows due to the yield stress, and consequently displacement for viscoplastic displacements is very low in terms of the efficiency. But our results in viscoplastic displacements in rotating pipes will show that we can have a very large displacement efficiency when you apply rotation. The experimental setup is identical to the previous one, except for that for the light fluid, we use a Kabapol solution for which the rheology can be described by the Herschel-Balkley model. And for the yield stress, we are covering an order of magnitude of the values of the yield stress. So the dimensional and dimensionless parameter ranges are given here. We discussed earlier on dimensional analysis that there are 4 parameters that are mainly important: Rossby number, Froude number, Reynolds number, and Bingham number. And the Bingham number here is the effective Bingham number, based on what the literature suggests us. So the Bingham number only varies between 0 and 1. So it's always between 0 and 1. The flow is even with the 4 parameters, is still very complex to analyze for viscoplastic displacement. So we need to make some adjustments and some simplifications, starting with defining some characteristic stresses. So viscous inertia, viscous yield, inertia due to the impulse flow, buoyant, and inertia due to the rotation. So we are interested in flows in which, in the absence of rotation, static residual layers of the displaced fluid exist. So we assume that the viscous stress of the displacing fluid, that is basically moving this way, is much smaller than the displaced fluid yield stress. So to have basically the appearance of the static residual layers in the absence of the rotation, we assume that basically the inertial characteristic, inertial basically stress due to the impulse flow is larger than viscous stress, because we want to understand the effect of the impulse flow on how the displacement changes. We basically but assume that the inertial basically stress due to the impulse flow is still smaller than the yield stress, because we don't want to dominate the yield stress. We assume that the buoyancy and inertia are of comparable order, and we are also interested on understanding how the rotation basically affects the flow. So we are increasing tau r from 0 until the combination of tau r and tau I and its ratio to tau y become an order 1 parameter. So these are basically the limitations of the experiments and analysis. So let's jump into the results. Looking at the results at 0 rotation, the heavy fluid slumps underneath the light fluid, leaving behind static residual layers of the displaced fluid in the absence of rotation. By increasing the rotation, decreasing the Rossby number, we observe that these static residual layer thicknesses decrease, and at a critical rotation, basically, you more or less remove all the static residual layers. So, and the flow patterns won't be much affected by a further increase in the rotation. So the flow can be divided in terms of inefficient and efficient displacement flow regimes. And this is my last slide, main slide. So if we put the data points in terms of the efficient and inefficient displacement flow regimes in the same plane that we introduced earlier, Fruit number and Fruit over Rossby number, we can observe that the data points are reasonably segregated using these dimensionless groups. But interestingly, the line that we found for the Newtonian transition, the critical transition for the Newtonian fluid, seems to be still more or less, not perfectly, but more or less valid for basically classifying the flow to inefficient and efficient removal regime. So on the other hand, and this is actually a bit bizarre. So on the other hand, if we plot the value of the Bingham number on the same graph, we observe that the large values of the Bingham number could exist in this region, which is basically the region where we have efficient displacement. So we need to explain why the static residual layers can be displaced for such flows. So to do so, we have plotted the total rotational stress, which is composed of the rotational inertia and impulse inertia, and this ratio to the yield stress on the same graph. And we are marking on this graph the small values of this ratio, smaller than 1/5. And what we observe that the majority of the data above the critical line, which is the efficient removal regime, they show the large ratio of the total inertial stress ratio, total inertial stress to the yield stress. And this basically justifies why the basically rotation leads to the removal of the static residual layers. And finally, if we plot the iso lines of the constant Rossby number on the same graph, we can see that by increasing the Fruit number, the flow transitions from efficient to inefficient displacement flow. And by finding a line that is perpendicular to the transition line that we found, we can sort of find the fastest route of the transition from inefficient to efficient displacement flow. And this would basically minimize the energy that you put in the system. So with that, I would like to end my summary, end my presentation. And because I'm right at the 46 minutes, I would like to just leave the summary of the presentations and take your comments, questions, feedback on this recent work that we have been doing. And I appreciate being invited for this fantastic series. Thank you.